What I want to do is show you this project here. Go to the project at the top of the 127 page and go down to the first Windows ED308. This is kind of a long project, but I'm going to demonstrate at least the main parts of it here. What we're going to do here is exploit this thing called Vulnerable Server, which is a deliberately vulnerable Windows application written by a guy, I think Stephen Bradshaw, just for the purpose of training people about security, and it's really very good. So we're going to learn all the important tools here. Basic Python scripting, which is nothing more than what you've already done in the Linux exploitation, how to use the Immunity Debugger and the Mona plugin, which go together, and the Metasploit framework we've already used, and something called NASM shell that we're only going to use a little bit. So the main thing you're going to do here is learn how to use the Immunity Debugger. That's the main new thing here. And of course, you should be using virtual machines on your private network because a Vuln server is of course unsafe. It can be hacked by a bunch of techniques, so you shouldn't be running it on a real server or on a machine you love. So I've got a private cloud running here. Here's a Linux machine running Debian in my private cloud, and there's a Windows machine here. So a Windows machine has this address, 192.168.1130. I'm going to need that. And the Vuln server, you just download it and run it. It's already been downloaded on this machine. Download it, unzip it, and then just run vulnserver.exe. And now it started listening. So it's listening on that address on, I think, port 9000. And so the first thing we're going to do is connect to it from the Linux machine. And so I'm going to open those instructions elsewhere on my other screen so I can see them. And I'm going to also need to open them in here so I can copy code in. So let's go to samsclass.info and 127. Projects. Okay. And ED, all right, looks a little funny, but I think I get the right project here, ED30 something. There we are, ED308. All right. So, oh yes, there's a couple adjustments on your Windows machine, which I think have already been done. Make sure that you're set up for a client machine, not a server. So in the performance options, you turn data execution prevention only for essential Windows programs and services. Otherwise, it will block the kind of simple attack we're doing. This means that the stack is going to be executable, which we're going to run. So this is something that is turned off on servers by default in Windows, but for client versions like Windows 10 and Windows 11, it's typically on the lower settings so you can run old software, which is what you want. And if you change it, you have to restart your machine. You should have the firewall turned off, and you should have error reporting turned on if you just want to see the next box. This is not really that important, but turning off error reporting will give you more information when you crash a program, and we are going to crash this program quite a few times. So the vulnerable server is running like that. We found its IP address. Now we can test the server. So we can just do a netcat connection. I'll need that address again, which is, I think I ran a ping up here. There we go. That's the address of my Windows machine. If I ping it again, I see I'm reaching it. So now I just want a netcat on port 9000. So NC will connect to that machine. And I've shown on port 9000. It connects, maybe it was 8000. Let me check my instructions. 9999, okay. There we are, it works. Welcome to Vulnerable Server. I made it through, I'm going to give it help. And now it will show there are various things here available. These are just meaningless functions that are supposed to make it look sort of like an email server. These are just various functions that take various parameters, and they each have different vulnerabilities. So you can practice a whole lot of attacks here. The one we're going to use is trun, which is the one that has a simple stack-based buffer overflow, which is the one you start with. These other ones have other kinds of exploits, and we'll use those later. So now I'm going to exit. All right. So I connected to the server. I made sure that the networking is okay. Don't have a firewall in the way or anything. So now I can perform attacks. So first thing we got to do is fuzz the server. So I'm going to use this code. I'll copy that. Well, it's not listening to me when I right-click it. Or maybe Control-C will work. We'll see. Now, whoa, Control-C. Now let's try nano. fuzz1.py, and that paste doesn't work. How about Control V? No. All right. How about Shift Control V? Nope. All right. If I can't copy and paste, that's going to be annoying. How about right click? Paste. The copy is what didn't work. Perhaps I'm going to need a different browser or something. Right click, copy. Maybe there's some other way. Is there an edit somewhere to copy inside Firefox? Maybe Control C? Let's try Control C. All right. And now right click, paste. Ah, there we go. Okay. Now the only thing that's wrong is the address, which is 192.168.11.30, I think. All right. And so now it's going to... 190, thank you, 168. Good. All right. So now it's going to ask me for the length of an attack. Then it's just going to connect, which is what all this nonsense does in Python. And then it's going to send that many A's, however many you asked it, and then print whatever comes back. And then it's going to try to execute. It'll do trun space period, and then the A's, then a carriage return line feed, and then print whatever the server sends back, and then exit normally. That's what this is going to do. So if I save this with Control X, Y, enter, and then run it with Python 3 fuzz, I send it 10 A's, and it works. It sent 10 A's, it gave me the response trun complete, and then goodbye, so it didn't crash. So now I can just send more until it crashes. 100 doesn't make it crash. 1,000. Whoops, oh, I got to put 1,000 down here. 1,000 does not make it crash. So 2,000. 2,000, and it crashes. See, connection reset. It didn't say trun complete and goodbye. So now I know that 2,000 is enough to crash the server. So I found the first step, which is a denial of service attack. Now, I've lost my Twitch window here. Let's see if there are any chats. It is a vuln server. I've discovered GVim. Okay, I don't know what that is. Anyway, all right. Anyway, so that's the first step. I've now found the first vulnerability in the program, found a buffer overflow. All right, and it crashes at 2,000, and now on this Windows machine, I should see a message. Let's try that. Here's my Windows machine, and I might see a message telling me the program has crashed, but I might not. Perhaps the error reporting's not on this one. Doesn't really matter. You can see the box is gone. It has crashed. All right, like I said, that's not that important, because now we're going to run it in Immunity Debugger. This crash just told us we'd found a vulnerability, but to learn more about it, we need a debugger, just as we did on Linux. So instead of launching it again here, I'm going to run it in the debugger. So let me launch Immunity down here. And then I'm just going to open the file open to open vuln server. And since I've opened it recently, it's down here, downloads vuln server, vulnserver.exe. That loads it in the debugger. And now, if I maximize this, let's see, maximize. I don't like this. I'm not seeing the bottom of the window. There's the bottom of the window. Okay, fair enough. Let me just try and adjust this window so it's everything I need is visible. All right. And so here is the assembly language code to run. Here are the registers like ESP and EBP for the stack and so on. And here's the stack down here showing addresses and so on. So the main thing I wanted to see, look down the corner, right now it's paused. The program is not running, so you can't attack it. So yes, you can run it in Azure. Plant Data, you see this question, you can run it in Azure, and then you can attack it from a Linux machine in Azure. You can also expose it to the internet, and if you do, then that is risky, which you're probably okay. Just be aware somebody might hack your Azure machine, so just don't have anything private on there, like email or anything, and you may have to just regenerate your machine if somebody hacks it. All right. But this is not a commercial product running on a lot of servers, so I don't think there are automated attacks. So it's not very likely that someone will hack it. If you put up something really common, like a vulnerable version of WordPress, it really will get hacked within an hour. because there are just automated bots hunting for those. But this thing is only being used by students. Anyway, so now you have to run it. Here's run. And you might have to run it twice, depending on your situation, because it's 32-bit code running on a 64-bit platform. But in this case, running it once was enough to get it running. So now it's listening. So now I can send in my attack, which was, whoops, here. All right, so I can now send in my fuzz, for example, of 1,000, of 2,000, made it crash. Okay, and it crashed because it didn't answer. And if I look here, see down at the bottom, access violation when writing to 41, 41, 41, 41. And it's kind of small there, so let me mention something. If you can't see that box at the bottom, because sometimes it vanishes, you can view the log up here. And the log will show you the same message, and you see it down there in sort of a bigger font and everything. Access violation in writing to 41, 41, 41, 41. So I found a vulnerability. It caused the machine to crash, but it is not executing a code all full of A's. It's writing to a location all full of A's. And that's okay. We talked about it in the format string. If you can control a write operation, you can take over the box, but it's not as easy as if you control an execute operation. So even though this is a vulnerability, this is not the easiest vulnerability to exploit. So I'm going to debug restart and say, yes, I want to abandon this run. Now it's paused, so I have to hit the run button again. Now it's running. I'm going to just try a different fuzzing. A 2,000 caused a vulnerability, but it wasn't the simplest vulnerability to attack. Let's send 3,000 and see what that does. It also crashes, of course, but it doesn't crash the same way. Now, there was a different message down there, and like I said, sometimes it vanishes too fast to see it, so if the message is not showing up down there, you can hit view log to see it. And now here you see access violation when executing 41, 41, 41, 41. This is what we want. Somewhere in the 3,000 characters, 4 of those characters went into the instruction pointer and it tried to execute them. So I have direct control of the instruction pointer. This is a classic stack buffer overflow, where data I put in goes right in the instruction pointer. So this is the one to use. And sometimes putting in different lengths of data can hit different crashes, and that's what happened here. 3,000 A's caused this crash, 2,000 A's caused a different crash. So from now on, I have to make sure that every time I send any kind of attack, the total length is 3,000 and nothing else. If I change the length, I might go nuts because I'll hit a different vulnerability. I want to always hit the same crash and then learn how to exploit it. So I'm going to restart the server again. You're going to have to do this a lot of times and run it again. So now I can move on to the next attack. So now I've done the fuzzing and I found a vulnerability that's easy to exploit. So now the next thing I have to do is use a non-repeating pattern so I can find out which of those characters ended up in the instruction pointer. So I'm I sent 3,000 A's, we've already done all that. All right, now I'm going to create a non-repeating pattern of characters. And there are a lot of ways to do it. But what I did was this. I just wrote my own code to do it because it's pretty easy to do in Python. And I think I can just go to this one. Yeah, this one here is the one that does it. I think I called this EIP. VSEIP1 is what I called it. I don't really care about those names too much. All right, this is the code that sends a non-repeating pattern of characters. So we put this in and talk about it. All right, nano VSEIP1.py, and right-click, paste worked. And if I escape backslash, you go to the top, and I have to fix this address, which is 92.68.11 and 30. All right, so here it's going to send 1,000 A's, and then for I in 0, 1, 2, 3, 4, for J in these 10, and K in those 10, it's now going to make a series of, this is 10, 100, 500. It's going to make 500 blocks of 4 characters, which is the 3 digits, I, J, and K, and then a capital A. So that is going to add up to 2,000 characters. It's 500 blocks with 4 characters in each. And what it looks like, if you just print them out, I put it up here, it looks like this. You have 000A, 001A, 002A, 003A, and so on. And the point is, this way, any 4 bytes in a row will be uniquely findable in that list. There are many ways to do it. This is just the first way that occurred to me to do it. So instead of sending 3,000 A's, it sends 1,000 A's and then 2,000 non-repeating characters. So the total length is 3,000. And it just sends that to the same server the same way. So that should crash the server at the same crash, but now I should be able to tell which Python 3, now I should be able to tell which characters ended up in the instruction pointer. So I send that. The server crashes because it does not respond. It never says trun complete or goodbye. And so if I go here, at the bottom I see access violation when executing, 35, 32, 41, 31. And again, if you can't see it easily down there, you can view the log. And here it is. So it crashed at 35, 32, 41, 31. And, Latin 1, yes, exactly. Latin 1 is the Python 3 to convert bytecode to printed bytes. It's not technically ASCII, but yeah, I know what you mean. That's what you have to do to send raw bytes that might not be printable in Python 3. And this, by the way, 31 is a 1, 41 is a capital A, so this is 1A25, and the letters are backwards. So the instruction pointer had the pattern 1A25, and you can see that. If I go back to the instructions, if I figure out how to get there, not on the Windows machine, that's why. All right, let's go back to the instructions, which are here. All right, so 1A25 is here, 1A25, in that so you can figure out this is 000A is a group of 4, so this is, you had 250A, so that's 250 groups of 4, so at this point you had 1,000 characters, and so that's a little bit more than 1,000. So anyway, figuring it out, it was 1,006 bytes in. So the thing that will target the EIP precisely is this one, which I think I call VS EIP2, all right? Let me put that one in. Control C will copy. And I got to get rid of this. Okay, nano VS EIP3 apparently is what I called it. All right. And I got to go to the top and change the address. $30. There we are. Good. All right. And so now I have 2006 A's, then BCDE. I'm trying to get the BCDE to go in the instruction pointer, and then I put enough F's to make the total 3,000. Because the total length has to always be the same. And so this is just checking to make sure I really control the instruction pointer. Those 4 letters should go in the instruction pointer if I've done it right. So I need to restart my server. On my Windows machine, I just crashed this server and it's paused. So I have to do debug, restart. And yes, that reloads it, but it's paused. I have to hit run to run it. Now it's listening. Now I can go back and run this. Python 3, VS, EIP3, and again it crashes, of course, because I sent a 3,000 character thing. And now I saw at the bottom what I needed to see, but once again it vanished out of this stupid window. It does that a lot. I don't really understand why, but view log will bring it back. So now you see it was when executing 45, 44, 43, 42, and that is B, C, D, E backwards. So I now know exactly how to control the instruction pointer. So I now control the instruction pointer, so the next thing I have to do is put in dummy shell code and see if I can run it. So I'll prepare this again, reload it and running, and now go back here and look at my instructions again. So now I'm going to put in examine the memory at ESP. I could have done that. Yeah, that would be, that's true. That's right, I'm going to have to deal with address space layout randomization. So let me just run that attack again to point out this. This is an important point I didn't think about. We're just going to run the same attack again. All right. So now if you look at your Windows machine, whoops, I got to get here. Okay. It's crashed. And now see the ESP is here. And if you move this over so you can see it, see the ESP is pointing to FFFFF. And here's some A's that hit EBP, and here's the BCDE that hit EIP. So let's take a look at the memory in the region of ESP. So I'm going to highlight this, right-click, and follow in dump. Like I say, the whole point of this dump down here is you can examine any memory region you like. And now if I scroll up just a little, you'll see here's all the A's, here's the BCDE for the EIP, and the right next character is an F, and that's what the ESP points to. This is really handy because this machine is a modern Windows machine. It's running on Windows 10. It has address-based layout randomization turned on, and you can't turn it off. So I can't jump to an arbitrary memory location. It's moving all the time in memory, every time you restart this program. So I can't jump to a fixed address, but I don't have to. I can jump to ESP, and ESP will point right to these Fs, and I control these Fs. So it'll point to my code wherever it is. So this is how I'm going to overcome address-based layout randomization. I'm going to put my exploit starting here in the Fs, and then find an instruction to jump ESP that doesn't move. And that's called trampolining. This is the simplest case of return-oriented programming. I jump to code that will jump back to wherever my code is, even though I don't know that address. All right, so now I'm going to debug restart. And run it again, so it's ready. And now, go back to here. All right, now there is the same problem, of course, of bad characters. Like we said before, characters that terminate the string, like null, line feeds, carriage return, and space, will typically terminate it. So you can do a test to check for bad characters, the same as we've done before, where you send just all the characters from 0 to 256 in there, 0 to 255, and see how many of them get in. And the end result is you learn what the bad characters are. I'm not going to do it live, but it's part of the project. So when you're done, it turns out that I think the only bad character is null. Yep, the first byte is null, none of the other characters, right. The null is a bad character, okay. So then you had to try again for bad characters, and I think the next time all the bytes appeared. So in this case, the only bad character is null. You can use all the other 255. So that's handy. So now we gotta find assembly code that we can use for our trampoline to get back. And the way you do that is you use Mona. Mona is an optional additional thing you add into Immunity. So you have to go download a Mona from GitHub and then drag it into the right folder on your machine with Immunity installed, which is this folder, C program files, x86, Immunity Inc., Immunity Debugger, PyCommands. So you have to put it in there. That's where Immunity will find extra code, extra Python commands that are running. And I've already done that. And after that, you can run Mona. So Mona lets you look inside programs to find out what modules are available and to find trampoline to overcome address-based layout randomization. So the bang Mona is how you start it, bang Mona. And for modules, you just type in modules, and then it will show you the modules in this program, which is very handy. So this is showing me, I need to scroll to the right if I can figure out how to do it. Whoops. Let's see if I can get this to scroll without going nuts on me. Click in there. I try scrolling left and right and it doesn't work. I don't seem to have a scroll bar anywhere that will work. So what I'm going to do, I think, is put it in Notepad. Let's try that. Let's highlight it all. It won't highlight, huh? All right, I'll look at my instructions. I'd have to resize this to make it small for the video. I'm going to look at my instructions where you can see it. All right, so here, what this Mona thing does is it shows you all the modules. And so here you see a dill, another dill, here's kernel base.dill, here's a lot of things. These are all the various functions, and it tells you what security features are turned on for each one. It tells you the addresses, and it tells you if they've been rebased, if they're using something called Safe Structured Exception Handler, which we'll talk about later, address-based layout randomization, and so on. And the main thing we care about right now is address-based layout randomization. If everything was really randomized, we would have a really hard time doing any of these exploits. But it turns out that not everything is randomized. You can see there are two modules with false here. One here and one here. So these modules are not randomized. But this one here is loaded in low memory. This is the main executable for vuln server, and it is loaded, like I said in the lecture, at 400,000. So the first byte is always a null, 00, and then 400,000. So you can't use these because those addresses include nulls. But there's another one, which is the DIL library, the custom DIL called ESSfunc.dil. That one is also not randomized, and it's loaded at 62,500,000, so there's a lot of addresses in there that don't contain null bytes. So we know this function has fixed memory locations, and all we need to do is find a jump ESP in there. And so there's a way to do that, and that's this, mona jump -r ESP in the module ESSfunc.dil. This will find us the addresses in that function that, that contain jump ESPs. So, get rid of this and put in that. Didn't listen, okay, doesn't like it. I tried to carry a clipboard from the other machine. I have to type all this junk here is the only way to do it. I'm trying to copy from a Linux machine to a Windows machine, and I don't have that ability. All right, there's the command I want. Let me see if I can get this to move. Oh, there we are. Good. I can put it down there. And now I can get back to my Windows machine. All right, and now it's gone. All right. It was there and it moved somehow. Let me see if I can get it to stop moving around on me. Nope, it keeps jumping back up. All right, maybe I can scroll it down. The problem with graphical environments of cloud machines. This is why I really prefer command line environments. But with Windows, you really need to use a graphic environment. All right, I'm getting close to it now. There we are. Now I can see what I want to type in. It keeps jumping back because it just exists to drive me nuts. All right, so let's see if I can get it. Mona, bang Mona, jump -r ESP -m, and I think I remember the rest is sfunc.dil. I think that will do it. This will search through that function for jump ESP commands. And the answer comes in the log, which vanishes because Windows exists to drive us all crazy. And here you are. Here's some jump ESPs. There's 9 jump ESPs in that function. So any of these addresses will do, and the first one will be fine, 6250.11af. The only thing I care about is it doesn't contain any null bytes, and it doesn't. So now I know how to do it. Okay. Now, all right, I think I've already got Metasploit installed. Let me just check and make sure that's true. If I go to my terminal, let's see if I have MSF Venom. And I do. Okay, good. It's already installed. That's what I wanted. Good. So now, I found those locations. So now I want to test code execution. This is going to be VSEIP3. This is all paralleling the stuff we've done on Linux. So let me go back to here, and let's see what I have. Okay, let's call that EIP3. I must have been call it 2. Let's call that move VS EIP3 to VS EIP2. Okay, and nano. All right, and now paste in this stuff and go to the top and change the address. 92, 168, 11, and 30. All right, so what this is going to do is send 2006s. Now it's going to put in that address, 6250.11af, which will point to a jump ESP. Now I can put code to execute here. So I'm going to put in a NOP sled, 1690s, then a break, and then enough padding to fill it up to 3,000 total bytes. So if the trampoline works, I'll bounce off the trampoline into the NOPs, execute the NOPs, and hit the break. So I'll be able to see 2 things, if the trampoline works and if I can execute code on the stack. So this is what I'm, let's see what that does.
You're missing a parenthesis at the end.
What's that?
You're missing a parenthesis at the end.
I couldn't understand that. What?
You're missing a parenthesis
I'm missing a parentheses.
at the end.
At the end? At the end of the program? Okay, let me take a look. I might have failed to copy something. Oh, you're right. Thank you. Good. By the way, it'll never execute that command anyway. It's going to crash up here. But anyway, you're right. I was. Python might have complained about it. All right. So now let's make sure this is running, and it is. So let's run it Python 3, vs EIP3. Okay, there it goes. And there it crashed. This is good. And notice here, you can see the stack is now 90, 90, 90, and then there. Now it said int3 command at this address. This is very good. It hit an int3. So if I look at the registers, which are annoyingly, I don't know how I scroll sideways in that little pane there. That's pretty harsh. Oh, there. Okay, good. So now I can see EIP is here, EBP is here, ESP is there. Let's look near the instruction pointer, which is right here. Here's the instruction pointer. If I just scroll up a bit, I can see what happened here. And you can see that it worked. Here's the code I injected, 625011AF. That's the address. It jumped there, it came back, and then it executed nop, 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 int. And that's where it stopped. int3 command there at D8. So this proves I have all the essential features. I now know how to control the instruction pointer to get to this address, and I can execute instructions at that address. So now all I have to do is replace this fake code with a real exploit, and I'll be able to run it. So I'm going to debug, restart, and say yes, and then run it again so it's ready for another attack. And now I can move on to run a real attack. So I'm going to need to get real exploit code. So first I'm going to get a dummy here. This is going to be VS shell. This is going to open a shell. So first I'm going to get most of the code prepared. Control C, all right. And now I want to get to the terminal here. All right, so nano VS shell. All right, and paste in that stuff. All right, and go to the top. Okay, 192, same old thing. $68, 11, and 30. Okay, and now I've got a NOP sled and the trampoline, and now I just need to put in my exploit, which is going to be a buffer, and I have to get that from Metasploit. So to do that, I need to get my IP address, and I need to put it in this command. So I'm going to copy this one, which is kind of annoying to type. Okay, and now let's get back to our terminal. So first, get the IP address. The IP address of my command and control server here is 192.168.11.6. So now I want to put in the Metasploit command that will generate the payload. And that's the only adjustment I have to make. I have to fix that address to the right address. So it's 192.168, 11, and 6, I think. Yeah, it's still on the screen at 6. Okay, so what's going on is, this is going to create a Windows Meterpreter reverse TCP. So it's going to phone from the Windows machine back to the command and control server, and to get controlled to this location and that port number, and it's going to avoid using null bytes and give me Python code. So that should create the buffer I need. Okay, there it is. Now I just need to highlight this and copy it. Okay, there it is. I can do edit, copy, and now I should be able to put it in my file, which is this one here. And down here, I should be able to paste it in. It did not copy because this thing exists to irritate me. All right. Somehow that command line did not copy correctly. Let's see if I can figure out how to get out of this. Control X, N. Okay, I need a copy from this terminal. I think Shift Control C might do it. I'm surprised the edit didn't work. I wonder if right-click would do it. Right-click, copy. That's reassuring. Perhaps right-click paste will work now. No. Well, all right. Now I'm going to get out of here without saving changes. There's another way to do it. I could redirect it to a file and insert a file using the commands. Yeah, I don't know what gvim is. Apparently there's some other editor I could be using. There's some way to copy here. All right, there's some way to put output. Let's do this. Output to foo. There. That'll put it in a file named foo. And there's a way to insert with, if I knew what gvim was, that might be good. It's all because when I'm using these cloud machines, the command control keys and everything are not being sent correctly up there. Anyway, now there's a file called foo. Now I can nano this one, and there is a way to insert the contents of a file. Read file, Control R, foo. There we go. That amounts to the same thing. All right, this will get through the day. So now I've got the NOP sled, I've got my buffer here, which is Metasploit shellcode. And now I got my padding to make it up to 3,000. So this is pretty good. Let's see if this works. This should give me a shell on the machine. So I do Control X, Y, Enter. Now, I need to start a listener on this machine. So we've inserted the exploit code. Okay, now we start a listener, which is this stuff, MSF console. It has to be sudo also. So let's go here and see if I can make these down here. In fact, the first part I have to do separately, but the rest of this I could copy and paste. All right, so I do sudo. I'm going to need a new terminal. Let's have a new tab. Yeah, new tab would do. All right, good. So sudo MSF console, the other part of Metasploit that makes a listener. All right. Okay, and now I should be able to paste in those commands. There we go. And this tells it which exploit I'm using, Windows Meterpreter Reverse TCP. It's a handler. It's going to listen on every IP address on port 443. So now it's listening for incoming traffic from the Windows machine. And I can send the attack here by just sending this Python 3 VS shell. This will run the exploit on the Windows machine. Python 3. So there it goes. And here, it's working. It's got a handler. It's sending stage 1. There, stage it over. So I can do sysinfo. And it'll tell me I'm on a Windows machine. This is my Linux machine, but I'm in control of the Windows machine now. This program is still running, but I have control. And so I can do help and, see various things here. I could try to elevate myself to system and get the passwords off the machine and so on. But, now I control the Windows machine. That was the point here. And that's it for this project. So this shows you all the steps you need to take over Windows machine in the simplest case. And all we're going to do is have variations on this as we do other kinds of attacks. So that's the only demo I needed to give you today. Let me stop the recording.